Hello, F Sharp. Welcome back. We are continuing our journey of writing a fast dictionary in F Sharp. Last time what we did is we attacked the problem of allocations occurring while looking up items in our dictionary. I mean, to be quite honest, looking up an item in a dictionary needs to be incredibly fast. And if you're doing any kind of allocation in that process, that is frankly absurd. So we absolutely had to get rid of that. Now, what I want to do, though, is address a problem that we probably wouldn't see unless we did some testing with the input values for our keys that we're using in our dictionary. And right now, what you're seeing on the screen is the results of our previous benchmarking. And we're saying, like, okay, for integer keys, we're now essentially as good as the .NET dictionary. I know in this case, the .NET dictionary did not do as well. I think that was some kind of fluke that happened with, I'm not sure exactly what happened there, but I'm not counting that one because it looks like for some reason the .NET runtime thought it had to do allocation here for some reason. Very strange. On the string side, we still have a performance gap for our smaller ones, but for these longer ones, it looks like we're closer. So we will attack this performance gap. But before I do that, I want to address this problem that I said that is this kind of hiding in our dictionary. And so what we're going to do is we are going to go and look at our code. And last time what we did was we were working on zero allocation. Let me zoom in here. And to do a lookup in the dictionary, you take the key, you get the hash code for the key, which is some random integer, and then you need to map that integer to one of the buckets in our backing array. Now, in our case, our arrays are always going to be, the size of our arrays are always going to be powers of 2, and that's going to be really important coming up in a bit. Not everyone does that. People take different approaches, and it's for this problem that we're about to see. Right now, this is where we're computing the hash code and we're masking the bits to make sure that it's a positive integer. And then we are using a mod operation to figure out which bucket in our backing array that we need to go and look into. Now, there's a huge problem with this, and I will show you what that problem is right now. I'm going to go to domain in my fast dictionary test benchmark project, and I'm going to change the keys that are getting randomly generated. Right now, the keys are being, first of all, we're generating the exact same set of random keys every single time because we're creating our random number generator with a seed. The values for our integer keys are between 0 and 100,000. Now what I'm going to do, though, is I'm going to comment that out, and I'm going to uncomment this line. And what this is doing is it's bit shifting all of those values to the left. And that is the same as multiplying. When you do bit shifting in base 2, it's the same as multiplying. And I'm actually going to make this, really bad. I'm going to make this 16. So this is the same as multiplying, this bit shifting. What is this doing? Well, before our keys were this kind of random numbers between 0 and 100,000. But when we do this bit shift, since that operation has occurred to all of our keys, they now have a pattern to them. There's now a very distinct pattern to our keys because we've done this bit shift to every single value. So now when I go to try to run the benchmark, I'm going to try to run this exact same benchmark again. Let's see what happens. And I mean, I'll cut to the chase. I mean, it's going to try to start up. And then when it starts up, it's going to say, hey, before anything else, and then nothing's going to happen. It's just hanging. And what's actually happening is my computer is working really hard to try to get this benchmark up and running, but nothing, it's not going anywhere. Why is that? That's a great question. So part of this channel is I teach you how to diagnose these things. And so I'm going to now turn to one of my favorite tools for profiling, and it's super luminal. Previously I've used .trace, which is a great tool. I think that superluminal does a better job of illustrating the problem here. So no shade for .trace. I still love it, still use it, but I think this one kind of lets you see it more distinctly. So I'm going to go ahead and run. And what I'm doing is I'm saying, hey, go run that benchmark code, and I want you to run it, thousands and thousands of times. Well, fortunately, we're not going to need it to run thousands and thousands of times to see what's going on. And so, okay, it's starting up the profiling code. It's gathering information on what is taking so long. I'm just going to let this run for a sec. Okay, now I'm going to start analyzing it and say, okay, what the heck was going on? Where were we spending all that time when the benchmark was spinning up at the beginning? And what we see here is, I should probably have another video just kind of understanding superluminal output. They have some great videos, so you go check it out. But we have all these different threads that are up and running. This is for the .NET runtime. So these are not our threads. Only this top thread is our thread. So we're going to hide all these other ones because we do not care about them right now. We only care about our thread. And what we're going to do is we're going to expand it out. And so now what we can see is a little bit of a inverted flame graph, however you want to look at them. And we could see like all the different things. This is kind of like different stack traces across time. And so we can see our benchmark is starting to run. And I'm going to go ahead and zoom in. Let's go ahead and zoom in here and see what's going on. So now I'm just looking at that section. I want to zoom in. Okay. I am narrowing my focus here. So I'm looking at a narrower slice of time because the top is a timeline. And so startup code, zero allocation. You zoom in some more. So it's trying to start up right now. Zero allocation loop. So here's the nice thing I see. I'm in the fast dictionary, zero allocation dictionary constructor. So I'm spending all this time in the constructor here. Why is it spending so much time in the constructor? That's what this is saying. It's like all these calls down below are inside the call to create an instance of the zero allocation dictionary constructor. So now what I'm going to do is I'm going to use another one of my favorite tools. Well, favorite aspects of this tool is I'm going to look at the call graph. And right now it is showing you every single gory detail of the .NET runtime and what is going on here. That's one thing that's kind of nice about .trace is that it kind of filters this away for you, but I still like seeing all the detail because we are all about the details on this channel. And I'm going to go down and I'm looking at inclusive time. So it's how much time our program is spending in that method call. And I'm going to go all the way down here, main profile, and this is what I'm going to do is I'm going to right click on this and say that, hey, I want to set this as the root. So like this is the top level thing I want to be looking at. So now we're kind of zoomed in. We're just looking at the constructor and the calls that the constructor makes. And there's this other button here, which is expand the hop path. So superluminal will automatically just kind of open up the methods where you're spending the most time. And it's here. So we're inside the loop, and Jit new, we are spending all this time doing all this like GC stuff. Like, what the heck is going on? Why is this happening? So what is happening? When this is trying to insert items into our dictionary, it's going to a bucket and then it's like adding to the list that's at that bucket. We'll deal with the fact that we're using a linked list later, but it's constantly trying to add to those linked lists. And ideally in a dictionary, we're spreading that out across our array. But what would happen if all of our keys were mapping to the exact same bucket every single time? Our dictionary would essentially be turning into a linked list, which does not have the performance characteristics we're looking for. So that Bitshift thing, what is that doing to our keys and what is that doing to our code? I want to show you what that is doing. There it is. So this is I'm going to zoom out just a scotch. So this is the same code that we were using to randomly generate our keys. And let's say we have an array of, let's say it's 32. And I'm going to go ahead, and what this is going to do is like, hey, this is the same, create this exact same random number generator with the exact same key, the exact same seed. It has the same range of min and max key. I'm going to generate 10 keys, and I'm going to say, like, what if my backing array is 32 in size? So I have 32 buckets that I need to map into from values of 0 to 31. And now I'm going to generate those bit shifted keys. Well, okay, well, first of all, let's do it without the bit shift and see what happens. So I'm going to generate the keys, and then I'm going to compute the buckets those keys would correspond to in my code. And when I do that the first time, I see this. Oh, this is kind of nice. These are the buckets. The values are 23, 29, 18, 12, 21, 31, 4, 23, 14, 0. So kind of like you kind of uniformly distributed. Okay, now what happens when I put that bit shift back in? When I put the bit shift back in, okay, now those keys are all mapping to a bucket of 0. So what's happening in our constructor is because we've done this bit shift of 16, we've kind of put a pattern on our data, and our function for mapping hash codes to buckets is not robust against this kind of behavior. Now, this is actually where, this is a way that you can have like kind of denial of service attacks, is like if the attacker knows something about the dictionaries that your code is using and like what functions using for mapping those to buckets, this is a great way to create a denial of service attack, because you're making dictionaries behave like linked lists, which is very bad. So we need a different way, a more robust way of mapping keys to the backing array of our dictionary. Now, I like to cite all my sources, and I'm going to come back and mention this talk again, which is fantastic. And if you haven't figured it out by now, all of my content is basically me having a performance problem, going and looking at what the C and C++ community is doing, and then translating that to F#. So I don't actually do anything creative. I'm looking at what the real performance people are doing and figuring out how to do that in F#, and then sharing it with you. So this talk is fantastic, and it's one that's inspired a lot of the ideas that we're covering in this series. So I highly recommend that you go and watch it. And the link will be below. But Multi also has a blog where he writes some really fantastic in-depth articles. And one of the things that he covered, and this actually this content is not in that YouTube video. So you got to go and read this. And again, I will link to this as well. It's fantastic. And he talks about Fibonacci hashing. And Fibonacci hashing is this fantastic way of mapping. Well, yeah, it's another approach to hashing. It's multiplicative hashing, except that the multiplier that you're using is coming from Fibonacci numbers. And I won't go into the nitty-gritty detail of exactly how it works. You should read his article, and there's some videos in there that illustrate the idea. But essentially what it is like, hey, we're going to use a special magical number that comes from the Fibonacci sequence, and we're going to multiply our hash code by that number and then do a bit shift operation to get an index into our array. And that code looks like, oh, that is VS Code. I want writer. That code looks like, and I'm going to Fibonacci hashing now, it looks like this. Where what I'm doing is, again, I am computing the hash code for that key, and then am casting it to an unsigned int and multiplying it by this magical number. What is this magical number? Where does it come from? Well, I'll show you. I come back to Chrome, Firefox, and I put this in. It's 2 to the power 32 divided by phi. Now, phi is the golden ratio, which is where the Fibonacci numbers are coming from. And 2 to the 32 is the range of values for an 32-bit int. And when I do that division, I get this number that I want to use for multiplying my hash codes by. Now, if you want the deep mathematical theory, go read the blog post. It's fantastic. So when it comes to our code, that's where this magical, apparently magical number is coming from. We perform this multiplication, and then what we do is we bit shift that result. And so this multiplication is giving us a nice, really random unsigned int32. And so that new number is going to be uniformly distributed over the unsigned int32s. But when I index into my array of buckets, I want a number that's going to be between 0 and the length of that array. And so the way I do that is because my buckets array is always going to be a power of 2. It starts at 4. As you can see here, I start with 4, an array of 4 elements. And every time I resize, I double that. So the next time I resize, I'll go to 8 buckets, then to 16, then to 32 and 64, and on and on. So I know this will always be a power of 2. And so I then can use a bit shift. And what I do is I say, like, okay, I want to take the top n bits that will allow me to index into this buckets array. And the number of bits that I need for that indexing is computed this way, where I take 64. Hi, sorry for the jump. I realized I had a small bug in my code, so I wanted to go back and fix it. Before I had a 64 here, it should have been a 32. It's been fixed now, so let's continue. So what we're doing here is we're doing this multiplication, and then what we do is we only want the number of bits necessary for getting a numbered index into our backing buckets array. And so the way we're doing that is we're saying, hey, take 32 and then subtract the trailing 0 count from the length of our buckets array. And the reason for that is because it's powers of 2. And so we know there's only going to be 1 in that integer bit representation, and the number of zeros after it will tell us how many bits we need to be able to address that size of that array. I might do another video longer to talk more about that in detail, but suffice it to say, this is the way we can say, like, this is how many bits we need to get an integer that's in the range of values that we actually need for indexing into our bucket array. So we get that and we do this bit shift. And so when we use this logic for computing our buckets array, let's go back to VS Code and see what happens when we use that logic. And I'm going to uncomment that, comment this, and then I'm going to run this all again and see what we get. Dun, dun, dun. And so now what you see is that the Fibonacci buckets are kind of spread all over the range of values now, 9, 15, 24, 25. They're not all mapping to 0. And even though we have the same pattern in our data, the Fibonacci hashing is robust against that. And so now we've protected ourselves from what would be a really serious problem had we not addressed it here really early on. So there's another bonus for this, though, and it's in performance. Now let's look at the assembly that we were using when we used this mod approach. And so right now, what I'm showing you is I'm using sharplab.io, which is an amazing website where you can put F# or C# code in, and then you can get the assembly that gets generated for it. And you can actually look at, hey, do I want to look at the IL? Do I want to look at the C# that would have been generated? It's fantastic. So it's a great way of taking small snippets of code and seeing, okay, what does that compile down to at the end of the day? Now, mod approach is that idea of like, hey, we have a hash code and we need to map that into an array. And so that's what this operation would be. And then we can see what the resulting x86 assembly would be for that. We have a move. We have this kind of cast to a double here. We have this I divide, so an integer division. and then this move. Okay, so move single instruction, cast single instruction, move single instruction, I divide. Integer division. Let's look at, so now I'm looking at Agner-Fogg's table of instructions. And Agner-Fogg is this crazy, crazy genius who goes through and does this intricate profiling of CPUs to figure out how long all these different instructions actually take. From what I know, Intel and I'm not sure Intel and AMD actually publish their numbers officially. So Agner-Fogg is not like affiliated with Intel or AMD. So this is good stuff. So if we go and look up integer division, and I'm specifically looking at my CPU. So I have a Zen 2 processor. And so it's going to depend on your CPU, but kind of generally they're approximately the same-ish, but you might see some, if you're using some of the more esoteric x86 instructions, you might see a greater divergence in performance. But we're looking at we're looking at a Zen 2, and we're looking at the I divide for a 32-bit. I'm gonna go ahead and zoom in a little bit for you. I divide 32-bit. This is taking, that operation takes between 13 and 28 instructions. Let me double check that. Yep, ops latency. Yep, 13 to 28 CPU cycles before that result is available to you. That's less than ideal. I'll put it that way, because this is like the very core part of our loop. Like every time we look up a value, we're going to have to perform this instruction. And so 13 to 28 CPU cycles, not terrible, but it would be great if this was faster. Now, when we compare that to the Fibonacci hashing approach, so this is what that F# equivalent code would be. We got this integer multiplication and then a bit shift. And then we come over here and we say like, hey, that's an integer multiplication. And then this is again a bit shift is what this instruction is. It's HRX. This bit shifts are single operations. I'm not aware of a bit shift that takes more than a single CPU cycle. I multiply. Let's go look up how integer multiplication in here. And if it's right up here for a 32-bit, they are all here it is. 3 instructions. 3 CPU cycles versus 13 to 28 CPU cycles. So massively faster. And again, like you might think like, Matthew, this is absurd. Like I perhaps there's a video I watched a long time ago, back when Microsoft had Channel 9.msdn, and I was talking about it. The guy was talking about like data warehouses and data sizes, and he made a comment that just stuck with me. And he was a British guy, and he said, if you mind the pennies, the pounds take care of themselves. And the idea is like, if you are careful in the small things, then the performance of the big things will just happen by themselves. And so dictionary lookups are so critical for performance that anything that slows them down is really going to end up having this massive effect across all of your code, and you may not see it because it's just pervasive. It's just everywhere. It's just like, it's not a single method call that you're making. You're making this call millions and billions of times in your code. And so like that penalty, that cost, that slowdown is just spread out so far, you may never see it, which is why I was really interested in doing this series and really diving into the engineering of a .NET dictionary. So this is awesome. By going from a mod-based approach to this multiplicative hashing using a Fibonacci number, we have a dramatic performance improvement just in computing, just mapping that hash code down to which bucket we're going to look stuff up into. And so I had to rerun these benchmarks. They're not quite done, so I'm going to skip ahead now to when these benchmarks are actually completed and we can look at the results. And now we have our results of using Fibonacci hashing for our dictionary. And what we're seeing is we're getting some really fantastic results at this point. I mean, for integer key type, key counts of 10, 100, 1000, we were faster. For 10,000, we were slower. And then for strings, we're competitive, but certainly not better. And we still have this like 1 byte allocation. Again, I have not tracked down exactly what's going on there, but I will figure that out. But what we're seeing is that we've done better. And what's more important is we're still using that same set of integer keys that have been bit shifted, but our dictionary is no longer sensitive to that pattern. And so now we have a more robust way of mapping hash codes to buckets in our backing dictionary. So we've protected ourselves against something, and so now we've kind of cleared the way of these problems, and now we're going to be able to really start drilling into performance and looking at different approaches for storing entries into a dictionary. So thank you very much for spending some time with me today. I really appreciate it. I hope you got some value out of it. Please, if you have any questions, comment, email, message me. I'd love to help it out. Thank you very much. Bye-bye.